Hello and welcome everyone to our virtual session. This is Asma Saidi. I'm the secretary of the EAGE local chapter, and I will be the moderator for today's session. Before we start, please note that the session is being recorded and it will be uploaded to our social media platforms, such as YouTube. Also, during the session, please note down your question because there will be a Q&A at the end of the session. Now, let me introduce our presenter for today's webinar. He is Dr. Mohammad Abdullah, an assistant professor at Kuwait University and College of Engineering and Petroleum. He is a highly skilled petroleum engineer with a strong academic background and industry experience. He has 2 master's degrees, the first one in petroleum engineer from Pennsylvania State University, and the second one is in Reservoir and Geoscience Engineering from IFB School in Paris. And recently he got his PhD in Petroleum Engineer from University of Texas at Austin in Enhanced Oil Recovery. He worked in KOC, Shell, and Total Energies, so he has an experience in industries. Currently, he is working as an assistant professor at Kuwait University, and he is actively involved in teaching and research. He has published around 8 papers in SPE. He's focusing on development of particular tools for enhanced oil recovery and field implementation, particularly in the areas of polymer, gel, foam, and sufficient application. And now, we will start the session. So, Dr. Mohammad, the floor is yours.
Thank you, Asma. Just checking the voice is good.
Yes, Dr. It's clear.
Okay. So first, let me start by thanking EAGE Kuwait chapter for this invitation. I hope to deliver some interesting stuff regarding polymer. So the topic today will be, can viscoelastic polymers reduce oil saturation or residual oil saturation? We'll have an implication there into field insight and practical applications. So main questions will be there. Just don't worry, I will take you all the way from the fundamentals, all the way we're going to build up on that, all the way to viscoelastic and so on. So main questions we're trying to answer: why polymer flooding? We start by this. Then what are the types of polymers? And what's the viscoelastic polymer? So what's so special about these polymers? Lab evidence on reducing residual oil saturation by viscoelastic polymers. Then we're going to move from the lab into the field and trying to check how viscoelastic polymers impact injectivity of the injectors as well as oil recovery. So we start by a simpler question: why water flooding, right? So if we're looking at the y-axis in here, which is a well rate and years of reproduction, normally we'll start producing by natural depletion, which is based on the pressure into our reservoir, and we'll have natural depletion. We'll deplete that reservoir. In order for us to keep producing, we will inject some water to continue the production of the oil, right? Just like here, if I have an injector and a producer, I'll inject some water. Usually, I like to make analogy of this, just like if I have a balloon, which is my reservoir. By natural depletion, as much as it loses pressure, it will deflate. What I'm trying to do by water flooding is inflate back that reservoir and keep the pressure there, so you keep producing from your reservoir. Okay. So now we answer the first question: why water flooding? Once we look at the water flooding, now we'll look at the reservoir. We have an injector and a producer with a top view. My green is my oil, and water will be that blue in the schematic. When you inject water normally, water viscosity is quite low. Let's say it's only 1 centipoise compared to oil viscosity. Normally, oil viscosity, it varies widely, but it can be tens and orders of magnitude higher than the water viscosity, as well as the heterogeneity or the geological heterogeneity, let's say, of the reservoir. That will give me some channeling and non-piston-like view of the sweeping of the oil. So you'll have an early breakthrough, taking the easiest channel between injector and a producer. Now, if we take a cross section between injector and producer, and assuming we do have different permeabilities. Here, K's refer to permeabilities. For example, K3 is the highest permeability, and you inject from this side, you'll have the earliest breakthrough into K3, and you kind of circulating the water and not much producing of the oil. This phenomena, usually we regard it toward favorable or unfavorable mobility ratio. Mobility ratio, simply, it's whatever you are injecting as a fluid in terms of permeability and its viscosity. For example, here we have water. We'll have the viscosity of the water divided by the oil, right? So we're trying to push the oil somehow. So if you have higher than 1, this mobility ratio, you end up with such weak sweep efficiency per se. What do we do? Now let's look at the polymers. And why do we do the polymers? First, polymers usually, they are that thick, viscous liquids, just like, the hair gels, polymers. It's very similar to this. Like, they're very viscous, and they increase the viscosity of the aqueous phase, which is a key word in here, because we said if we want to have some favorable mobility, you increase the viscosity of the aqueous phase, which is water in here. Once you increase it, you decrease the mobility ratio. If it's less than 1, we call it favorable. What will happen here? Again, if you look at top view, injector and a producer, you will have a nice kind of piston-like or stable flow that's moving. This is the water that's moving the oil in the front of it. Similarly, if you have a cross-section, you have a better sweep and enhancement in the sweep, even if you have multiple layers with different permeabilities. To wrap up this part, in terms of comparison, we'll look again here. This is when I have a polymer, how is it really sweeping my oil? And this is without the polymer. When I have a water viscosity, and the water viscosity is quite low compared to the oil viscosity. Similarly, with a cross-section, if I have a polymer, it's a much better sweep efficiency compared to have an early breakthrough if you have water being injected. Now, we discuss why do we do polymer flooding. Now, a very important point in here. Conventionally thinking, if I have an oil recovery on the y-axis compared to how much per volume to be injected, like water per volume to be injected, okay? Or aqueous phase per volume to be injected. Conventionally thinking, polymer flooding in the dark blue curve in here, it will end up with the same ultimate recovery factor compared to water flood. So it will not have an additional recovery factor. It will only accelerate the recovery. So less amount of per volume to be injected, and you will recover much more oil at the end. But if you keep injecting water, you will end up ultimately with the same ultimate recovery factor. So polymer recovers the same amount of movable oil, but by water flooding, but faster. Digging deep into this phenomena, usually we describe it in reservoir engineering or petroleum by the capillary number, which are the forces that control how much oil is trapped in your pores. So if I have a residual oil saturation of oil plotted against that capillary number, the capillary number will have the viscous forces, like the viscosity, as well as the velocity, compared to interfacial forces. And in polymer flooding, usually we just change the viscosity, let's say from 1 centipoise to 10 centipoise or so. No matter how much we change it normally, we will stay within that range that we don't really exceed 10 minus 5 of capillary number. Capillary number is dimensionless number, so it's described just as a number. So usually we don't really exceed 10 minus 5, which means we cannot reduce the residual oil saturation beyond the water flooding residual oil saturation. We can decrease it or go through this curve by other enhanced oil recovery mechanisms that, for example, will change interfacial tensions orders of magnitude to change from 10 minus 5 to all the way to 10 minus 3 to see sharp decline. So water flooding, it only accelerates the water flooding, polymer flooding only accelerates water flooding, and it should not conventionally introduce any additional oil compared to water flood, right? So it only targets movable oil. I will talk now about the types of polymers, okay? Normally or conventionally, there are two types of polymers we discuss. Biopolymers, I'm not going to discuss in here, and synthetic polymer, start for HPAM. This is hydrolyzed polyacrylamide, right? These synthetic polymers, what's very important in here, they are flexible coil. The structure is very flexible and it's just like a coil, right? This is a key word that will be repeated over and over and will control everything that's coming in the coming slides. You know, the feasibility, being able to produce that synthetic polymer, give it all the advantages compared to biopolymers. That's why synthetic polymers is what's usually used in enhanced, let's say, the reservoir, let's say for the sweep efficiency improvement and field implementation. You would rarely find biopolymers being used. They're more costly and vulnerable to biodegradation that we're not going to talk about. So we're here focusing about these flexible polymers. They're just like coils. Let's see what we're going to happen. So the other questions, okay, how would polymer increase the viscosity? What really happened in the structure of polymer that give you that viscosity? Usually, in simple terms, there are two groups in terms of chemical structure, amide group and carboxylated group. Usually, carboxylated groups comes from the amide groups, okay? And in the carboxylated group, there is that negative charge on the oxygen that we're seeing in here. That negative charge will give you the repulsion in the molecular structure. So if you have repulsion in the molecular structure, it means it will spread out, right? A very interesting way to think of viscosity. If you have a block, right? If it's spread out, it means you will have more restriction to flow. If you have more restriction to flow, it means you have higher viscosity. Opposite to this, if I have sodium, which is if I add some salt, it has Na, which is sodium, that's positively charged. It will be attracted to these negative charges on the polymers, and then you will have the polymer molecules shrinking. If it shrink, it's less space and less restriction to flow, so you will have less viscosity. So now we describe how would really polymer give you that kind of viscosity. You will have the negative charges, right? The negative charges will give you repulsion and the molecular structure. The more repulsion you will have, more restriction, more viscosity. And the opposite, if you have a shield impact, they call shield effect, by some salinity being added, you will have it kind of, let's say, just compressed or shrinking the molecular structure, less restriction to flow, less viscosity. Okay. Next, an important phenomenon. Probably most of us know this. Polymer is non-Newtonian, which means it's a function of shear rate or velocity. If I have the viscosity being plotted against the shear rate or velocity, what will happen, we know that structure that we talked about, that coily shape of polymer. If I put it in streams, that they're straight streams, or just like the rheometer I'm having here, it's rotating in straight streams. What will happen, it will disentangle my molecular structure. So it will straighten out, will just make it straight. And instead of having that coiling shape, it will just straighten out that molecular structure, just like here. And then you will have a shear thinning, reduction in my viscosity, right? So whenever I have an increase in velocity or shear rate, it will disentangle it, and then you will have reduction in the viscosity. This is important to think of. Do we always have this phenomena, and where do we have it? Normally, we would have these in the labs when we have a rheometer, because it's going in streams and straight kind of streams per se. Or if you have some pipes, right? If you have pipes, they're moving straight in the pipes. Or if you have fractures, because, you know, most of you are probably a geologist or so, fractures are just like pipes into the reservoirs or so. So even in the fractures, there is a common understanding, or let's say consensus, that polymers act in shear thinning behavior if you have fractures under the reservoir. This is very important to keep in mind because it will be coming up later to us. Okay. Now, very interesting to see opposite to what's happening or what's expected. How would the polymer rheology change in the porous media? What we're having here, the X's, right, is whatever being measured in the rheometer in the lab, right? These are the X's. You have a shear thinning behavior with a shear rate increase. But what happens in the porous media, if I do put this in a core flood and increase the velocity or shear rate, you will see an increase in the viscosity. Instead of going to shear thinning, we call it shear thickening behavior. Okay? This is very important phenomena. And to understand it more, what's happening in the porous media, you remember that molecular shape of the coiled polymers that we're having? It moves with a certain velocity into the pore throats, right? And goes into coiling and decoiling. Remember this coil that we talked about? So it will stretch. If it's moving too fast through the pore throat, does not have much time to recoil back, just like this shape in here that's moving through the pore throat and got stuck while it's kind of stretched, what will happen, you will have impedance to flow translated into viscosity. Again, we said whenever we have that shape kind of giving us stretched, it will give us impedance to flow translated into viscosity. We call it elongational viscoelastic behavior. Elongational viscoelastic behavior. Elongated polymers can bridge the pore throats, just like similar to what's happening in here in that schematic. Now, more into the polymer rheology in porous media. Another question will be, okay, how about in the reservoir? What's going to happen and where that shear thickening behavior, increase of viscosity will occur? Remember, we were having the same plot of viscosity versus velocity or shear rate. We had a shear thinning. This is what we expected at bulk rheology, or what's going to happen in the lab, compared to shear thickening in the porous media. Whenever you increase the velocity, and guess what? The highest velocity is closer to the injector. If you are a distant 0.1 all the way to the 10 feet or so, this is where you would expect the shear thickening to occur. So this will raise a very valid question. How about the injectivity itself? If I do have probably expecting 5 centipoise, now we're having 150 or 160 centipoise. Am I really be able to inject such? Are the pumps capable of such injection? Or would I suffer in my reservoir closer to my injector? So would I suffer of any injectivity problems due to polymer viscoelasticity? Let's see. Okay. So to quantify or to understand the viscoelasticity itself, there is an agreement. There is a dimensionless number called Dipper number. What it really describes, that Dipper number, simply relaxation time. That relaxation time, that coil, when I stretch it, the time it takes to recoil back, this is what we call it relaxation time to relax back. Compared to the residence time. Residence time is described by the time the polymer moves through that probe throats, right? This is a Dipper number. So what's important in here, not the equation itself, because some of us may hate the equations. If time to recoil back, relaxation time, is greater than the residence time, which means whenever it's coiling, it does not have, whenever it decoil to open up, it does not have time to come back. This is when the time to recoil is greater than residence time. Then viscoelasticity occurs. You will have a Dipper number greater than 1. You will have this greater than 1 when you have your relaxation time higher than your residence time. There is some consensus per se how to describe relaxation time. There are different ways of measuring it, but an interesting way, you remember that curve, you will have shear thinning if you have a bulk rheology, then you have a shear thickening increase in the porous media. They say the point where these two deviate from each other, I can take it as a relaxation time. You take 1 over the onset shear rate. Onset is where you'll have that deviation between these two plots per se. 1 over the shear rate will give you seconds, right? Because shear rate is 1 over seconds. So 1 over that shear rate will give you a value for relaxation time. And relaxation time is a function of polymer concentration, molecular weight, salinities, and other parameters. Okay, so why we're talking about this is very interesting. Now we'll see some lab evidence on reducing residual oil saturation by viscoelastic polymers. This is Chi 2017, our friends from UT Austin with Dr. Balhofer Group and Gary Pope. What they did, remember we talked about this graph, right? This is residual oil saturation versus capillary number. They kept a constant capillary number, that's 10 to minus 5 or so, while they injected, you see oil saturation here versus pore volume. In the blue, they injected lots of pore volume of water. Then they injected glycerin. What's a glycerin? It's a Newtonian fluid. Let's assume it's just like water with higher viscosity. Why would they do so? Because they want to differentiate the impact of increasing viscosity from viscoelasticity, in the sense that here I'm injecting a higher viscosity than water, because we said if I continue injecting water for infinite number of pore volumes, it will end up the same impact of polymer. Why? Because viscosity is higher. So they said, okay, let's differentiate the impact of only viscosity increase from viscoelasticity. Okay, so what they did after injecting around 9 pore volume of water, they injected a higher viscosity Newtonian fluid, glycerin in green. After that, they injected a viscoelastic polymer with a Dipper number of 15. I remember we said viscoelasticity start after you exceed a Dipper number of 1, right? You will have that differentiation in the equation itself. So higher than 1, you have viscoelasticity. What they observed is there is an increase of around 6% recovery of residual oil. This is very interesting. 6% is not really something trivial to think of if you have huge reservoirs. Let's see if we can take this to the field. Before taking to the field, let's try to understand why would viscoelastic polymer be able to reduce residual oil saturation or trapped oil. right? We did understand why the viscosity increased by viscoelasticity. Now we want to understand why residual oil saturation decreases by viscoelasticity. Now, we have to be cautious because these are still hypotheses. There are different hypotheses, but one of the earliest, actually, by Wong 2010, was saying if I have the rock, these are the greens, then I have residual oil saturation droplets, which are the red, and then I inject only water flood, it will move in straight streams through the pore throats. Okay. But if I have these viscoelastic polymers, or the polymers with high molecular weight, these polymers, usually they are entangled. They're connected. Each molecular structure is connected to each other. So it will try to pull each structure together from different directions, just like here, right? It will pull up, right, and left. While it's pulling together the polymer structure, it will be able to strip out some of the trapped oil. So this is one of the hypotheses that there, because of that big molecular structure connected to each other, entangled, it will be able to get some of the trapped oil in its movement. Now, another hypothesis, this is supported by some microfluidic as well as lattice Boltzmann, some simulation in there to see how is it really the flow of the polymers, the streamlines of the polymers, okay? Again, the green here is just the grains, okay? The red is an oil droplets. If we zoom in here, let's see if I zoom in here, you'll see this is streamline that's moving for very slightly viscoelastic, almost, let's say, like a water. It's almost straight in there. So it's not really touching that oil droplet or trying to push it somehow. So it's kind of trapped in that pore throat. But if I have high Dupre number, high viscoelasticity in here, what will happen, something we called chaotic turbulence. This viscoelastic behavior, it moves in chaotic turbulence within itself. Now, this turbulence is different than the turbulence of flow by Rayleigh number. This is happening at low Rayleigh number just because of the elasticity that's moved slowly, the polymer itself. While it's moving chaotically, it's able to push out that droplet of oil that was trapped here all the way up. So this is the second hypothesis we talked about, but let me come up back to my hypothesis. Okay. So this is the second hypothesis, and then there are others. So what's happening? How has it really been able to reduce my residual oil saturation? Is because of that viscoelastic behavior, the way it's moving, pulling each other into molecular structure, or chaotically streamline that's happening, turbulence, elastic turbulence flow. It's able to strip out some of the trapped oil. These are two of the common hypotheses. How does a viscoelastic polymer reduce residual oil saturation below residual oil saturation of water? Now, we did understand what was happening. Based on this, and we did say there are different experiments with supporting reduction in residual oil saturation in the lab scale. Chi 2018 proposed an elastic desaturation curve, okay, that correlated Dupre number, okay, to residual oil saturation reduction. This is residual oil saturation reduction. How much I will have after injecting viscoelastic compared to how much I have only for water flood. And you see, if I have a Dupre number greater than 1, I will start to decline in terms of my residual oil saturation. And then they come up with certain correlation that being embedded into a reservoir simulator. Now this will take us to the field scale and reservoir scale. Did this really happen? What did they really observe? Okay. To move from lab to the field, we have two main questions. Can we reduce oil saturation below residual oil saturation to the water in the field? Second, is there an injectivity issue with shear thickening polymer viscosity? Remember this, we have an injector. If we're too close, we'll have too much viscosity in there. So are we going to observe injectivity? Is there being reported in the field? And let's see what happened. First, to answer the first question in terms of reducing residual oil saturation, one of the earliest claims and observations per se that they got additional oil recovery because of viscoelastic polymer behavior was by Wang 2010 in Dajing field. They observed in 1,000 wells when they increased the viscosity from 40 centipoise. Let me have my laser. Okay, from 40 centipoise all the way to the 150 to 300 centipoise, they got additional recovery factor, 20% compared to 12%. This is an additional of 8% recovery factor. If you know the Chinese field and so on, their economic limit is too low. They may go to a water cut of 99% and so on. So additional 8% is significant for Dajing field. What happened in terms of reservoir simulation, Chi 2018 tried to simulate viscoelastic polymers under favorable conditions. He assumed permeability average of 5 Darcy. You see here is the permeability distribution, It's around 5 Darcy in here. This is in millidarcy, 7,500 or so. Okay? Salinity 1,000 ppm, very low salinity to have high Dipra number. Very high polymer concentration, 4,000 ppm. High relaxation time, assuming very high Dipra number, very viscoelastic polymers, right? And he observed, compared to inelastic, this is the water flood you're going to observe in here. And then this is inelastic, which means without viscoelasticity, I have a polymer being injected. And then an elastic polymer injected. He got almost 12% increment in terms of recovery factor. This is a hypothetical reservoir per se, and very favorable conditions, and they have been able to prove that it could happen. Now, looking at the injectivity problem, this is part of our paper at UT in collaboration with Dr. Sirat from New Mexico. What we did to try, in Madsen field in Austria, right? They injected an HPAM 3630. This is a high molecular weight HPAM in a vertical well, 500 millidarcy, 16 feet of thickness for about 53 days. They calculated. So now what we try to do is, because we say, in the porous media, we should go for this viscosity, right? A shear thickening viscosity, a high viscosity. And we calculate the bottom hole pressure of the injector accordingly. But the problem that we face, the calculated injected bottom hole pressure based on viscoelastic polymer viscosity, that black curve, is 10 to 20 times the recorded field bottom hole pressure. Let's see here. This is my bottom hole pressure compared to time versus time. The field is the blue triangles in there. What they recorded around 2,000 psi. But what we calculated, according to the viscoelasticity, that was 10 to 20 times whatever they have recorded. So it was kind of bizarre for us. The only way we could history match whatever they recorded in terms of bottom hole pressure to assume a shear thinning behavior. Okay? At well bore, polymer viscosity is 160 centipoise if shear thickening, and only 5 centipoise if shear thinning. Now, why would we assume shear thinning? Because what we discovered and being proven, whenever they injected that polymer, fracture started to extend all the way to 100 to 100, between 100 to 200 feet in terms of length. So whenever you have fracture, if you recall what we said, you will go from shear thickening into a shear thinning behavior. Fractures, very similar to pipes behavior, very similar to bulk rheology behavior, right? And now a recent study, very interesting, with the Tracirite group, they actually did their literature review over 40 years of field cases for vertical wells. They have seen all of these vertical wells developed some sort of fractures around the well bores. So what's happening is that viscoelasticity and increasing the viscosity of the polymer, you inject, you create fractures, then you will see an enhancement in the injectivity, opposite to whatever you would expect. You would expect a deterioration in your injectivity. But because of these microfractures, hopefully they are controlled, you will see an enhancement in injectivity. That's why it's being reported in literature that over lots of polymer fields implementation, they didn't see any serious injectivity problems. One of the best explanation for this is the development of fractures around the well bore because of polymer viscoelasticity. Now, having said this, what we did, we said, okay, if I did develop fracture for that same field, how would the real impact increase in terms of residual oil saturation? What we saw, as a fracture is started, the in situ effective shear rates decreases from over thousands reciprocal second to about 1, right? If I see the effective shear rate, I have the shear rate on the left y-axis and the fracture length in red right axis. You will see whenever the fracture is initiated in terms of days, it just started, you will have your effective shear rate in the black drops from thousands all the way to almost 1's order of magnitude, right? As a result, the Dipper number, because we see it, Dipper number has to do with the effective shear rate, right? Reduces from hundreds to less than 3. We'll look at the second plot in here. We have on the right side still fracture length and the red that was happening in there. It increased with time. Whenever fracture length increased, on the left side, we have a Dipper number. Dipper number in the black, it will drop from close to 1,000 all the way close to 1. I remember we said, unless we're much higher than 1 in terms of Dipper number, we would not see additional recovery factor. That's why the additional recovery factor was 1 or less observed for that case that we tested in the Madsen field. So this is almost concluding my presentation. So you'll see this observation can explain the insignificant additional recovery factor, less than 1%, obtained from polymer viscoelasticity. So whenever I have fractures that are happening because of viscoelasticity, it will reduce the shear rate. The shear rate will reduce the Dipper number, and then you will not end up with any additional or significant additional recovery factor because of polymer viscoelasticity. Okay. So my key messages in here: reduction of SORW due to polymer viscoelasticity is supported by lab evidence. There is a lot of lab work that has been done there. But the question is, it really going to be transferred to the field or not? Polymer viscoelasticity is a crucial property to consider for polymer field injectivity, especially in vertical wells. Reducing SORW, residual oil saturation of water, in the field requires high polymer concentration, high molecular weights, high injection velocity, maybe even away from the injector. You need a lot of velocities and high permeability. Fractures initiated due to polymer viscoelasticity need to be within 1/3 the distance between injector and the producers. So it's very important to control the fractures length being initiated because of polymer viscoelasticity, not to exceed 1/3 the distance. Otherwise, you'll have a lot of deterioration in terms of sweep efficiency. That was the purpose of polymer flooding. Lastly, the improvement in injectivity by fracture initiation can counteract the improvement that you would expect in oil microscopic efficiency by polymer viscoelasticity. Let me conclude by acknowledgement. I would like to acknowledge EAGE Kuwait chapter for hosting this session, Dr. Randy Sirai from New Mexico Tech for his support, Dr. Matthew Balhoff from the University of Texas at Austin. Some references in there if anyone is interested to dig into this, the ones I use at least. And please don't hesitate to contact me for any questions and any opportunity for collaboration. Thank you for listening, and please feel free to ask any questions.
Thank you, Dr. Mohammad, for this excellent and interesting presentation. And now it's the time for Q&A. Please, if you have any question. I think, Ali, you can drop your question in the chat box, or you can...
Sorry, I cannot hear anything good now. Yeah, I think Ali is muted already. I don't know if he's asking, or is it in the chat? Yeah, I'm reading the question. I think this is Dr. Ali. Can we classify as inelastic versus inelastic HPAM? Classify. Okay, so can we classify HPAMs from elastic versus inelastic? Is this a question? Yes. Okay, so let's assume this is a question. Has similar behavior. Okay. Okay. So, okay, if I understood it well, the first question is, can we have HPAM to be inelastic and elastic, right? The answer is yes, right? For example, if you have a lower molecular weight HPAMs, you would expect it not to be actually viscoelastic. The other thing, if you may have lower concentrations, you may not have viscoelastic behavior. Actually, we have a good paper by Dr. Seawright. He has done the lab work on this recently. And then there are 3 or 4 papers in terms of the controlling parameters to have viscoelastic behavior. So the main question is, the main comment is this: some polymers are viscoelastic. Generally, not all of them are viscoelastic in terms of behavior. At certain conditions, they can be viscoelastic. Now, is biopolymer viscoelastic? As far as I know, what happened with a biopolymer, because that you have that coil shape and they call it semi-rigid shape, you don't have, you don't have that coil shape. You have a semi-rigid shape. Let's see if I have it in here. Yeah. Yeah. You see that kind of semi-rigid molecular structure, you will end up only shear thinning. You wouldn't expect any viscoelasticity in the porous media. And this has been well established, actually. That's why you will see Chafateau, I think 1986 or so, one of the earliest paper. They were all based on the biopolymers. Lots of correlations in the past were based on biopolymers. That's why now we're trying to update these for some synthetic polymer with viscoelastic behavior. So generally, you would not expect viscoelasticity by biopolymers. Let's see other questions. Oh,
I think Michelle has another question.
Sure.
Can you hear me?
Yes.
Yes, excellent job, Mohammad. I think it's very excellent explanation here. So the take-out message from this discussion is that the viscoelasticity will reduce the residual oil saturation due to the two hypotheses that you mentioned. But with in the presence of fracture, we will lose this,
Viscoelastic.
Viscoelastic.
Correct.
Isn't it?
Correct. So they're all controlled, connected to each other.
Yeah.
If I have fracture, all of a sudden I'm reducing the shear rate or velocity. If I reduce the shear rate, I will reduce the DIPRA number less than 1 or close to 1. So you wouldn't expect reduction in residual oil saturation. So this is kind of the high, let's say, what we claim in here. So they don't go together. If you have fractures, you'll end up losing any additional recovery factor due to polymer viscoelasticity.
So to get benefit from this reduction in residual oil saturation, we want to make sure that we don't initiate fracture in the reservoir.
Yeah.
Which is a huge challenge for us.
I mean, exactly. There are different ways of doing this. Okay. One, if you do have very high permeability, okay, you may expect some good DIPRA number. The other thing people are thinking of, now this is a Chevron claim so far, is if I do have a horizontal well, okay? But if I have a horizontal well, because you have that length, so the interstitial velocity will be less, right? So you will not have lots of delta P being built and so on. So you will not have fractures per se. But at the same time, if I don't have fracture, then I need to have a DIPRA number greater than 1. If you look at the equation, let's see the DIPRA number equation. Yeah, a DIPRA number equation. If I do have the shear rate to be low because of the horizontal well, then in order for me to have a DIPRA number high, I need the relaxation time for the polymer itself. So the properties of the polymer themselves to be very high, to be very viscoelastic, right? That coiling is just like a coil. You need it to take very long time to coil back. Yes. So it's either way kind of condition. So it would really require very meticulous design of polymers.
Yeah. Thank you. Excellent presentation, Mohammad. Thank you.
Any more question? I have a question, Doctor, for you.
Sure.
Is it applicable to use them in siliciclastic and carbonate rock? And does the wettability affect the role of those polymers?
Yeah.
And for the saline formations, for example, here we have in Kuwait, if it's 230,000 ppm, can we use them?
This is very good question, a very twisty one. So let's break it into parts, okay? First, would wettability really impact? This is very controversial question. Initially, they were thinking if you have an oil wet, you will have additional recovery factor. But UT, what they really claim, or what they really did, 90% or 99% of all the experiments have been done so far on water wet. Because whatever you have oil droplets being trapped in the small pores and the whole phenomena of turbulence and so on, for the trapped ones, trapped droplets in the small pores, which means you'll have a water wet. Now, they did do a couple of experiments on oil wet. It was inconclusive. Sometime it increased, sometime it didn't. So it's still an area of research, right? This is for the wettability. All right. Now, going to the carbonate, carbonate applies similar, right? Because carbonate sometimes usually you have it mixed with, oil with, and so on. So it may have such in terms of behavior, besides other problems of carbonates, related to retention, absorption, so many other problems, right? So let's just focus in terms of viscoelasticity. Let's assume carbonates goes into mix to oil with, and the same answer applies. I don't want to go into other parameters that impact water flooding and carbonates. All right. Now, if that satisfies this question, the other one is related to salinity. Now, what we did observe, okay, is that salinity reduces polymer viscoelasticity in general. And going 230,000 and so, there are sometimes, okay, it's a claim, but if I want to go only 230 directly, there are not too many polymers that would really be tolerant to such salinities. But a general answer, we would assume salinity will decrease viscoelasticity, right? 230 is very high, actually, 230,000 ppm. Would that answer your question?
Yes, clear, Doctor. Any more question? Yeah, I think that's all. Thank you, Doctor, again. And thank you all for attending our session. See you soon in our upcoming webinars. And thank you all. Thank you, Doctor.
Thank you so much. Thank you for having me.